Hello, welcome for those interested in computational linguistics research. Today I want to introduce a new system designed for semantic analysis of text. What makes this system unique is its ability to decipher the meaning of words that have multiple interpretations in the semantic dictionary. This task is known as word sense disambiguation. Let's jump right into it by opening the Google Colab notebook, where we'll demonstrate how the system works. You can find the link to the document and the GitHub repository for this project in the description below. Word sense disambiguation is a fascinating challenge in the field of natural language processing. While there are existing tools like the LESK algorithm in the NLTK library, they often fall short in terms of accuracy. On the other hand, deep neural networks offer improved precision in classification, but they come with hefty memory requirements. In this video, we'll explore an innovative method developed to tackle WSD challenges. This method optimizes memory usage without compromising accuracy, making it ideal for seamless integration into NLP tasks. We'll also discuss the importance of the BERT model and how modifications to datasets and dictionaries can enhance WSD accuracy. Stay tuned as we dive into the details and demonstrate the effectiveness of this method through a series of experiments. By the end of this video, you'll have a better understanding of how our solution addresses the challenges associated with WSD, offering a practical solution for integration into NLP applications. Many words, like table, have multiple meanings depending on the context. This is where word sense disambiguation comes in. It's a challenge in NLP that helps computers choose the right sense of a word. Imagine reading a sentence like, "Sherlock Holmes sat at the table." Traditionally, dictionaries like WordNet simply list the most common meaning first. In this case, it might define table as a data structure, not very helpful for understanding the scene. That's why WSD is crucial. It considers the surrounding words and context to pick the correct meaning. Here's where things get interesting. Existing tools like the LESK algorithm in NLTK can be inaccurate. Deep learning approaches offer better precision, but they require massive amounts of memory, making them impractical for many tasks. In this Colab notebook, we'll unveil an approach that tackles the memory limitations while achieving top-notch accuracy, making it perfect for real-world NLP applications. We'll also explore the role of the powerful BERT language model and how adjustments to datasets and dictionaries like WordNet can further enhance WSD performance. Let's dive into the Google Colab notebook that houses our solution. To initiate the program, simply navigate to the Runtime menu and select Run All. This process activates the solution's 7 distinct Colab chapters. Each chapter corresponds to a separate code section within the notebook. These chapters work in a defined sequence, visualized through a sequence diagram that you'll see in the notebook. While this video won't delve into the intricacies of the code, it will explain the principles governing the system's operation. This strategic overview empowers you to seamlessly assimilate this solution into your existing natural language processing framework, enhancing its capabilities and efficiency. Now, let's delve into the technical aspects of our solution. The first step is straightforward. Submit your text, clear and concise. Moving on to the second step, spacey annotations. With just a few lines of code, we leverage the spacey library to annotate our text, providing us with a comprehensive word table featuring part-of-speech annotations. Subsequently, we will enhance this table with additional information obtained from other libraries in subsequent steps. While spacey represents classic natural language processing methods that demand minimal computing resources, our next step, KerasNLP, epitomizes modern NLP utilizing pre-trained neural networks. The KerasNLP library offers a variety of pre-trained neural networks to choose from, with the BERT large network selected for this project. Passing our sentence through this library, we observe how the KerasNLP BERT module tokenizes our sentence, yielding a vector of 1024 numbers for each token. These vectors encode a wealth of valuable information, enabling the solution of numerous natural language problems. We will leverage these vectors later to address our word sense disambiguation problem. Our fourth step focuses on combining the results from KerasNLP with those from spaCy. To achieve this, we take each word from the spaCy table and find its corresponding index in the KerasNLP tokenization output. By doing so, we create a seamless connection between the classic NLP methods provided by spaCy and the neural network capabilities of KerasNLP. This integration allows us to leverage the best of both worlds. The fifth step is straightforward but crucial. We employ the NLTK WordNet library, a reliable resource for semantic information. Specifically, we use the LESK algorithm, which has been around for nearly 4 decades. Why? Well, the LESK algorithm isn't perfect and it occasionally makes mistakes. Our goal is to improve its accuracy. So for each word in our sentence, we find its synset value using the LESK algorithm. But that's not all. We also add 2 additional columns to our spaCy-generated word table. The first column contains the synset value determined by the LESK algorithm. The second column holds the synset value found as the first record in the WordNet dictionary. We call it the most frequent synset. Why the dual approach? The most frequent synset serves as a reliable reference for words that don't require WSD resolution. Meanwhile, the LESK value is used as reference to compare with the method we've developed during this project. In the pivotal 6th step, we delve into refining the outcomes of the word sense disambiguation module within the NLTK library. This step marks a departure from conventional approaches by introducing a novel concept yet to be explored in WSD endeavors. This innovative approach challenges the conventional notion of relying solely on the WordNet dictionary and its associated word annotations as the definitive benchmark, often referred to as the gold standard. Instead, we pivot towards leveraging a trained neural network as our gold standard. Our objective: to realign the WordNet lexicon to mirror the knowledge encapsulated within the neural network. Motivated by the remarkable achievements demonstrated by advanced neural networks like ChatGPT and other large language model architectures, we aim to optimize the WSD process, prioritizing efficiency and efficacy. While BERT, for instance, may possess a smaller footprint compared to ChatGPT, its capabilities in solving the WSD problem are noteworthy, especially in terms of energy efficiency. Our WSD solution is underpinned by 3 core principles. Firstly, we employ a novel approach by conducting k-nearest neighbor classification of embedded word vectors, not within the conventional high-dimensional space, but in a reduced 2, 5-dimensional space achieved through the application of the neighborhood component analysis algorithm during model training. Further insights into this methodology are detailed in a research paper, the link to which is provided below this video. Secondly, we meticulously scrutinize the data sets used in standard WSD tests, uncovering numerous data annotation errors within both training and evaluation data. These corrections are consolidated in a separate file available on the GitHub repository associated with this project. Lastly, the crux of our innovation lies in restructuring the connections within WordNet to align synset structures with the clusters of BERT neural network embedding vectors. This restructuring process is facilitated by a straightforward k-means clustering algorithm. Detailed elucidation of this approach can be found in the research paper accompanying this video, and all modifications to WordNet synset connections are documented in a file accessible via the project's GitHub page. The final step in the method we're presenting here is known as final classification. Essentially, this step serves as an opportunity to visually review the classification results. If any errors are identified, we can then modify the model itself by incorporating new data or adjusting WordNet synset relations. Think of it as a simplified version of the new word sense disambiguation (WSD) debug system, specifically designed to test the WSD model in debug mode. To illustrate this concept, let's consider an example. The sentence, Sherlock Holmes sat at the table. We don't need to solve the WSD problem for the phrase Sherlock Holmes because there's only one synset value in the WordNet dictionary. We obtained its definition using the NLTK library during the fifth step of our method. However, the noun phrase, the table, is more interesting. Both Lesk's algorithm and the most frequent synset selection rule from the NLTK library yield an invalid value, specifically, a data table. Our method, on the other hand, correctly identifies that the table refers to an object belonging to the furniture class. In the Colab document we've presented, you'll find graphical representations of synset classification results. For the word table, we observe two distinct groups of points, clearly separated. Each point in the graph corresponds to a separate sentence in the WordNet set of sentences. The first group contains sentences where the word table signifies a data table, while the second group includes sentences where table denotes furniture. Our example sentence falls within the group of points representing furniture, demonstrating how our model operates. As we conclude this method presentation, I encourage you to use the system and provide feedback if you encounter any errors. Your comments will help us fine-tune the model and address any observed issues.